So today we're going to talk about heat transfer, going over your heat transfer notes. 3 ways in which heat or energy is transferred. First one is radiation. This one, the energy is transferred through the electromagnetic spectrum. This one, electromagnetic spectrum, is on your reference table, page 14. Radio waves, X-rays, gamma rays, infrared waves, visible light rays, all those are radiation. So when the sun is out, it's radiating. The lights inside, it's radiating. Your body is radiating heat off. Alright, so that's all types of radiation. Majority of the radiation that reaches the earth is in the form of visible lights. Radiation actually radiates out in all directions, so 360 degrees. Next one, we're going to look at convection. Convection transfers energy, or usually heat, through currents. We talked about this one when we did plate tectonics, because you had convection currents in the asthenosphere. That was what was causing the plates to move. The driving force of convection currents is density. More dense sinks, less dense gets pushed upwards. Alright? So this one, it says less dense gets pushed upwards by cooler, more dense material. This is going to be really important for you when we do meteorology and we look at cold fronts and warm fronts. As it leaves the heat source, it cools and becomes more dense. This one, if you're thinking about a heater, the heater that's in the classroom, it's sucking that cooler, more dense air up in, it heats it up. As it heats it up, it forces it outwards. That air is warmer. It's going to get pushed upwards by the cooler, more dense air. Alright? As it's left its heat source, it cools down, it becomes more dense, and it will sink. So you get that, and then it gets sucked back in the heater, heated back up. It's less dense, gets forced upwards by the cooler, more dense air. And then as it leaves the heat source again, it cools, and it's just a cycle. Remember, heat or warm air does not rise, it gets displaced by cooler, more dense air. That's a misconception, unfortunately, you guys come with. So I want to do a really quick drawing on this one. I have my beaker. I have water in my beaker. I have my Bunsen burner, which you guys will have next year with Mr. Miller. It's got my flame. If my flame is on this side, this is my heat source. So I am warming up directly above my heat source. So my convection current is going to look like this. If same concept, got my water, I'm just going to move my Bunsen burner to the middle. So here, I'm going to make actually 2 convection currents. I'm heating up, so this is my heat source, becomes less dense, it's going to curve and go out that way. This one's going to curve and go this way. So I get 2 going this way. So wherever my heat source is, that's where it's going to get warmer. That's going to cause that to get pushed upwards. Once it's left the heat source, it gets cooler and it falls back down. Alright, so that's going to be my convection. Next, conduction. Now conduction's got a D in it. D, direct contact, molecule to molecule. So it needs to be touching. So if I'm looking at it, the flame, whatever it touches, actually is going to heat. So molecule by molecule, I'm heating my water up if I have a kettle. So inside, we'll say inside my tea kettle, here's my flame. That's heating the bottom of the kettle up. The water molecules that are touching are going to get heated. All right, conduction. The water molecules then touching those water molecules are going to get heated. So what's happening is I'm making this warmer than the water up here. All right, that's unstable, and that's going to get me back to my convection current. All right? So they all intertie together. My flame is my radiation, molecule by molecule touching and heating and transferring that energy. It's conduction. Once it's unstable and the warm is down here and the cooler is above, cooler is more dense, it's going to force that less dense water upwards. So there are my three ways that heat is transferred. Radiation, conduction, and convection. All right, looking at temperature. This one you guys will talk about next year in chemistry. Temperature, you're measuring the average amount of kinetic energy. Remember, kinetic energy, half mass times the velocity squared. All right, temperature with that one, your energy is more when the temperature is higher, more kinetic energy. So your direction of heat flow is always from high energy to low energy, or high temperature to lower temperature. Couple terms really quick. Heat source, heat sink. Heat source is where the heat is coming from, or the higher temperature. Heat sink is where the heat goes to, or the lower temperature. A unit of heat is a joule. 1 joule is the amount of energy needed to raise 1 gram of liquid water 1 degree Celsius. So it's all based on water. Specific heat is the amount of, same thing as your joule, but it's not just water. It's the amount of heat energy needed to raise 1 gram of a substance, any substance, 1 degree Celsius. Liquid water has the highest specific heat. If you're looking at your reference table, page 1, you will notice that water has the highest specific heat. So therefore, it takes longer to heat up and cool down than any of the other substances. The higher the specific heat, more energy needed to raise and lower. So the whole idea, if I take you right now, today is one of those nice warm, humid days that we have in Syracuse. It's 86 today. If I drop you in Lake Ontario is not 86. All right, the lake in the summertime is a lot cooler than the air of the land because the water is taking longer to heat up. All right, if I looked at, say, October, end of October, the water is retaining heat, so Lake Ontario is going to be warmer. This whole concept is the reason why we have lake effect snow. Because a cooler, dry air coming from Canada goes over Lake Ontario. It's retained the heat in the wintertime. It's more warm, it's more humid, picks up all that moisture, and then when it goes across land, land has a lower specific heat. So it's cooler in the wintertime. So all that moisture gets displaced, or it drops out. So we get lake effect snow. So all has to tie back into specific heat of water. All right, the law of conservation of energy states that energy cannot be created nor destroyed. It just gets transferred from one form to another. The whole idea is when you're going from potential energy, when we did the river, you had potential energy when it was high at the head, and as soon as it started moving, it went to kinetic. Once it slowed down, that kinetic went back into potential. So it's just forming from one energy type to another energy type. Latent heat of fusion. On your reference table, page 1. 334 joules for every gram. I'm going from a solid to a liquid or a liquid to solid. So if I have 100 grams of ice, it's going to take 33,400 joules to change it to liquid water. So you just multiply the 334 joules by every gram that you have. Latent heat of vaporization, same concept as latent heat of fusion. This one I'm going from a liquid to gas or gas to liquid. Notice it takes a lot more energy to go from a liquid to a gas or a gas to a liquid. This one is 2,260 joules for every gram. Same concept. If I have that 100 grams of water and I want to evaporate it, it's going to take 226,000 joules to evaporate that 100 grams of water. Or in reverse, it's going to take 226,000 joules to actually condense the 100 grams of water. All right, as you go up the heating curve from a solid to a liquid to gas, heat energy gets absorbed. You're taking it in from the environment. As you go down the heating curve from a gas to a liquid to a solid, you release that heat energy back to the environment. So this one ties into apple orchards. Apple orchards around here, if we had warm spring and then all of a sudden the temperature really drops, what you'll notice is they actually spray water around. They're spraying water around so the water actually hits onto the little buds, and then as the water will evaporate, it's actually giving heat off. So it's just going to keep that bud warm enough that it won't get destroyed. So that way their crops don't get destroyed. All right? So it actually ties into something surrounding you. Absorption. I'm taking in. I'm gaining energy from the electromagnetic spectrum. Darker, more rough surfaces absorb more visible light. All right? The lighter colors, the smoother surface, they tend to reflect more. So they're not going to absorb, they're going to reflect. So when you absorb more, your temperature increases. When you reflect, your temperature increases less. All right? So if I'm looking at rough surfaces versus a smooth surface, that rough surface, that texture, has more surface area. So I have more surface area for absorption to actually occur. So if I'm looking at a forest versus if I'm looking at a beach, the forest, the darker colors, the rougher texture is actually going to absorb more than the beach. Beach tends to reflect more. All right, it's important to know, remember, we said most of our energy from the sun comes in as visible light that actually hits the Earth's surface. That's a shorter wavelength. You're back on your reference table, page 14, under the electromagnetic spectrum. That shorter energy gets absorbed by objects on the Earth, the land, the building, whatever. Then it gets re-radiated as infrared energy. That's a longer wavelength. That's what's getting radiated out to space. Now, if I have clouds at night, the clouds will bounce that radiation back, keeping us warmer at night. So the clouds act as blankets, keeping us warmer at night. If I don't have those clouds at night, heat's able to escape, my temperatures drop. The reverse is going to happen during the day. The clouds will cause some of that energy to get reflected back. So it keeps us cooler during the day, because our heat source during the day is the sun. The heat source during the night is whatever absorbed all that energy during the day. All right, so if I have clouds during the day, we're cooler. Clouds at night keep us warmer. Now, if I'm looking at a greenhouse, how a greenhouse actually works, and I'm talking where they actually grow plants. We have that energy coming in as mostly visible light. It gets through that glass. It gets absorbed by those plants. It gets re-radiated as infrared. Problem is that infrared light cannot escape the greenhouse, can't go through the glass, so it gets reflected back. So a greenhouse is always kept warm. Insolation, breaking it down, insolation means incoming solar radiation. So that's the energy that we receive from the sun. This is going to tie back into your astronomy. Remember, I told you everything here this year ties together. So if I'm looking at radiation and temperature, as the temperature increases, so does the ability of that object to radiate or give off heat. The more you absorb, so the higher your temperatures, the more you can radiate. Also, you're going to radiate at a longer wavelength than you were absorbing. What we just mentioned about visible light and then getting absorbed and re-radiated as infrared. Intensity is the rate at which energy is being transferred. My unit, joules per second. The greater the intensity, the higher my temperature. Now, my intensity is going to be greatest when that sun or my heat source is directly above me, so at a 90-degree angle. Because what you're doing is you're concentrating that energy just right below you. The lower my angle, I'm dispersing that same amount of energy over a larger surface area. So it's less concentrated, it gets diluted. So remember, it's most intense directly above, lower angle, less intense, it gets diluted. So we need to look at factors that are going to affect my angle of insolation. Like I said, this is your astronomy. So I'm looking at my angle. If I look at seasons, during the wintertime, if we have our lowest angle of insolation. So that means we have our lowest intensity. Summertime, we have our highest angle. Now, it's not directly overhead of us. Remember, the only state that has the sun as the zenith, Hawaii. But it's going to be, for us, June 21st, around 71 degrees from the horizon. So that one's going to be when we have our greatest intensity. Obviously, our equinoxes are in the middle. So you're looking around, for us here in Central New York, around an angle of 48 from the horizon. Latitude. Back to astronomy. December 21st, most intense. The sun is directly overhead or at the zenith for the Tropic of Capricorn, which is 23.5 degrees south latitude. On your equinoxes, be it March 20th or 21st or September 22nd, 23rd, most intense, the sun is the zenith for the equator. June 21st, most intense, Tropic of Cancer, which is 23.5 degrees south latitude. That's where the sun is the zenith on that date. Duration of insolation. Now, going back to that one diagram that we had with astronomy, it had the celestial sphere. The higher the angle, the larger the arc. The larger the arc, the longer you had, or the more daylight you had. The more daylight you have, you're going to have a greater intensity for your solar noon. It's higher in the sky. So for us, it's highest in the sky, June 21st, solar noon. Lowest in the sky is going to be my sunset and my sunrise, just as the sun is coming to the horizon. So a time of day, most intense solar noon, least intense sunrise, sunset, lowest in the sky. Shape of the Earth. Because of the shape of the Earth, we get that curvature. There's only one latitude that can have the sun as a zenith per day. So with that one, we talked it's oscillating between 23.5 degrees south latitude on December 21st to 23.5 degrees north latitude on June 21st. So in between those, it's where it's going to have the most intensity for each particular day of the year. Alright, so we're looking at temperature and insolation. Remember, insolation, incoming solar radiation, the energy coming from the sun. So if I look at the summertime we have the greatest duration. As you notice, the sun is rising around 5 o'clock in the morning, it's up if you're up, and you're setting around 9 o'clock at night. So I got my longest amount of daylight, it's my highest angle, so it's my greatest intensity. Alright, with that combination, it gives the Earth more time in the northern hemisphere to our southern hemisphere, because right now it'll be our summer soon. It'll be their winter soon. All right, it gives us more time to absorb that visible light. The more energy or visible light you absorb, the more you can radiate as infrared. The more you radiate as infrared, the higher your temperature is. All right, so let's think about if I'm not considering cloud cover, wind, or if it's a cold front, warm front going through, those little variables. If I go with it's a cloudless night, no fronts going in, my coolest time of the day is right before sunrise. And that is because all night long you've been radiating or you've been giving off that heat you absorb during the day. So as you radiate, your temperature drops. The warmest time of day, a lot of people think it's solar noon because it's got the highest intensity. Not true. Because remember, all night long you've been radiating off heat, you've been giving it off. You get that lag time because now you got to reabsorb heat energy. Alright? So it's not going to be solar noon when it's most intense. It's actually usually mid-afternoon. So the whole idea is you keep absorbing until the sun is setting. So with that one, my warmest time of day, mid-afternoon. Now mid-afternoon on the clock is going to vary with your seasons. Because remember, your sun is going to set around 9 o'clock in June, but around 4:30 in December. So mid-afternoon is going to vary time-wise. So for today's high temperature is supposed to be 89 degrees, and that's supposed to be at 5 o'clock in the afternoon. You've been absorbing through solar noon, even into like later in the afternoon. You hit your high, and as the angle decreases, you have less intensity, so you're not absorbing as much. You're starting to radiate a little less. A little more. You're radiating more. Clouds at night, I already talked about this one. Keep us warmer. Clouds during the day, keep heat out. It's going to keep us a little cooler. Alright, you need to go, how is actually air heated? Here's the sun. The sun radiates heat energy. That actually gets absorbed by the ground or buildings or whatever is out there, trees. Remember, majority of the radiation reaching the earth is visible light. That thing gets re-radiated as infrared. It's going to heat up molecule by molecule or conduction, the air above it. Once the air above it is warmer than, well, once the air above the land is warmer than the air above the air up here, you're unstable. So the lower atmosphere is less dense than the upper atmosphere there. So you get that convection current because the less dense gets pushed upwards by the cooler, more dense air. Remember, as you leave your heat source, you start cooling down, you become more dense, and you're going to sink. So it all comes back from radiation of the sun. The sun is our major source of energy. Heats us up, heats the earth up, surfaces. That gets re-radiated infrared, molecule by molecule through conduction. All right, the warmer air is below the cooler air. Unstable, so that's going to cause convection currents to happen. So we're back to your conduction, convection, and radiation. Okay, let's do a little 8th grade review. Really important that you remember this one, because this is going to tie into meteorology. Temperature and pressure are inversely related. Well, what's inversely mean? So inversely means opposite. So as the temperature increases, the pressure is going to decrease. As the temperature decreases, the pressure is going to increase. So what one variable does, the other does the opposite. So that's what inversely related. Also important for you to know, winds blow from high to low pressure, high energy to low energy, all right? So blowing from high pressure to low pressure, this, like I said, it's going to tie back to your meteorology. Or forward to your meteorology, I should say. This is your foundation. All right, we need to talk sea breeze and land breeze. I need you going back. It's during the day, the sun is out, here's my land, here's my water. Which one heats up faster? Well, it's the land, because it has a lower specific heat. So this one's going to be warmer. And this one's going to be cooler. We just talked about how temperature and pressure are inversely related. So if it's a warmer temperature, it's going to have a lower pressure. And if it was a cooler temperature, it would have a higher pressure. So also just noted, winds blow from high pressure to low pressure. So my wind is going to blow from the water towards the land during the day. That's what a sea breeze is. All right? Cooler, warmer during the day, because it has a higher specific heat, takes longer to heat up. So it's got a higher pressure. So sea breeze. During the night, I'll put a full moon for you, peaking at midnight. So with that one, it's my land breeze. Land has lower specific heat, so it will radiate off heat quicker. So during the night, this is going to cool down above the land. The water having a higher specific heat takes more energy and time to lose that heat. So that's actually going to retain its retain its temperature. So it's going to be warmer at night. Again, remember, temperature and pressure are inversely related. Cooler land is going to have a higher pressure. Warmer water is going to have a lower pressure. Winds blow from high pressure, low pressure, or from the land to the water. That's known as a land breeze. That's at night. Remember, this one, lower specific heat, loses heat quicker than the water. So the air above it's going to get cooler than the air above the water. Temperature and pressure inversely related. Winds blow from high pressure to low pressure. Land breeze. All right, hopefully you remember all this, because like I said, it's all going to intertie. As you saw, some of your astronomy came back, and this is going to tie into your meteorology, which is your very last topic. All right, good luck. Hopefully I see you at Google Meet.